welcome to this video on high-performance computing for Ansys Mechanical. This is part 2 of a multi-part series, and the main focus of today's video is to help users understand the basics of mechanical HPC and how to use HPC to speed up their mechanical simulations. My name is Jeff Beisheim, and I'm a Senior Principal R&D Engineer at Ansys, and I'm joined today by Herbert Gutler, who is the owner and founder of MicroConsult. Ansys has been collaborating with MicroConsult for over 15 years on the specific topic of HPC for the Ansys Mechanical product. And Herbert has a lot of expertise in this area, as you will see.
MicroConsult is a simulation services company, so our main focus is on thermal mechanical simulations on the device level, like MEMS or electronic packages, and on the system level when the devices are combined into an electronic control unit. We often deal with models consisting of hundreds of separate bodies and highly nonlinear problems due to contacts and complex material models. Working in the field of more than 20 years, we want to share our experience how to use mechanical HPC to dramatically reduce simulation runtimes.
So, anytime we start thinking about HPC for mechanical simulations, the very first thing we have to think about is hardware. And that's why we did the part 1 of this series, where we dedicated the entire video to talking about setting up a cluster that has well-balanced hardware for mechanical simulations. So Herbert, if you could maybe just briefly recap the important details of setting up a cluster for mechanical simulations.
Okay, so the purpose of this little picture in the right side is that it gives you an idea that the weakest part always dictates the performance that could be achieved, meaning that you can add as much CPU cores as you want. If the limiting factor is the memory, then this additional CPU cores will be very helpful. And the same is with a hard drive or with an interconnect. So you have to understand what's the limiting factor by studying the log files, for example, and then adjust the weakest hardware point to be no longer a limiting factor.
All right, thank you, Herbert, for recapping why hardware is so important to get good scaling with mechanical HPC. But one of the next things I wanted to cover are the different aspects from the software perspective when thinking about high-performance computing and mechanical simulations. So way back in 1990, Ansys was able to start supporting what's called shared memory parallel. So this was first available in version 4.3, and this is using multiple cores within a single box. Roughly a decade later, around the turn of the century, Ansys first introduced distributed memory parallel in mechanical APDL, starting in version 6. And this supports multiple cores on a single machine, but also supports running on a cluster. Roughly a decade after that, the GPU acceleration feature was introduced, and this allows some of the key solver calculations to be offloaded onto GPUs, and this is another form of HPC. And then most recently, around 2021, the concept of hybrid parallel was introduced in mechanical APDL. Hybrid parallel allows customers to blend both SMP, shared memory parallel, and distributed memory parallel within the same mechanical simulation. So from this, you can see there's quite a bit of options when considering HPC, and we're going to talk in more detail about each of these and the pros and cons and benefits that customers can expect to receive when using these different forms of software parallelism. All right, so for this slide, I set up sort of an image or diagram to kind of help better explain how shared memory parallelism works within the Ansys Mechanical APDL software. So we've got this image of a workstation, or it could be a single node of a cluster. And here we're considering in this workstation or compute node that we've got 2 sockets, and each socket would have 32 CPU cores. So in this situation, for using shared memory parallel, the finite element simulation is going to launch one process, and within that one process, it is going to be running multiple cores to achieve parallel computations. So in this case, there's no MPI software that's needed because all of these threads and all the computations are done within a single memory address space. So here we're going to have one thread running on each of the 1 CPU cores.
Okay, I mean, that kind of setup worked rather well when we didn't have 60 or 128 cores per CPU socket, but the higher the number of cores is getting, the more inefficient this way of handling data and running the simulation is going to be. So that was the first approach almost 20 years ago to get this going, but in the end it turns out it has to be something different when you run on a higher number of cores or in a distributed fashion on a cluster.
All right, exactly, Herbert. This speedups using shared memory parallelism can be very limited, and so There are pros and cons to this approach, and one of the advantages of using shared memory parallelism is that it does not increase the memory requirements as more CPU cores are used to achieve faster solution times. However, it's got major limitations in that one, it cannot run across machines. It does not support parallel computations on a cluster. And our speedups, as we just said, are quite minimal. We generally do not see significant benefit from using more than 16 threads, even if there are more cores within your workstation compute node. And so from an HPC perspective, the value of using shared memory parallelism is quite limited. Okay, so this slide talks about how distributed memory parallel works within Ansys Mechanical. So here we've got a typical layout of what it would look like to run a distributed memory parallel simulation on a cluster.
Okay, so what's different now is, and these are the dashed lines, that we have multiple compute nodes next to each other. And the second innovation is that we now have a so-called message passing interface working to organize the data transfer between the different compute nodes and the different processes running on these compute nodes. The advantage is that when using this kind of setup, you can combine a large number, and we're talking here about thousands of processes if you push it to the limits, to distribute the work across a cluster and thus improve the performance by orders of magnitude. Okay, so this distributed memory parallel option has been the working horse for us for the last 15 years, meaning that we started out with a rather small number of cores, but over the years we have built different clusters with up to 1,500 cores. And it's the default parallel method for many years because it's very stable and very reliable. It provides optimal scaling even when used on a single machine. And we see significant speedups beyond 1,000 cores, and if we really want. Of course, when there's light, there's also darkness, meaning you have to pay for the increased number of cores with an increased memory requirement. So you have to make sure that the cluster is equipped with enough memory to do these kind of simulations in an efficient way. Okay, so this is from a delamination study on an electronic device. We had a rather complex model, but that needed a high mesh density, so we ended up with some 8.2 million degrees of freedom for this model. It's a nonlinear transient analysis, so we have creep and nonlinear geometry effects. And this ran on a Linux cluster with Xeon Sapphire Rapids hardware. The message here is we ran this on several number of cores, so started with 60, and then 120, 240, 480, and so forth. So we have a log scale on the x-axis for the number of CPU cores. And the vertical axis is a speed up number, so basically we compared how much time we spent running it on this configuration versus the others. So a speed up of 2 would mean a double in performance, halving of the compute calculation time when running on this different setup. And what you can see from this line here is that for the first attempts up to, let's say, 480 cores, we have a basically ideal scaling behavior. It levels a bit off at the higher core counts, but remember we are here way beyond 1,000 cores. So we see a speed up between a single node and 20 compute nodes of about a factor of 15.
Okay, so now I'd like to shift gears and talk about one of the newest forms of parallel processing in mechanical APDL that is called hybrid parallel. So this, again, is a combination of distributed memory parallel and shared memory parallel. So here we have the same sort of cluster configuration that we've been talking about on the previous slides. And as Herbert pointed out, each of the dashed line boxes represents a compute node that has 2 sockets and 32 cores per socket. And so in this particular configuration that is displayed here, we have one MPI process per socket and multiple, or in this case, 32 threads utilizing all of the CPU cores within each socket. And so we still need MPI software to facilitate the communication of data between the multiple processes running within each compute node and across the multiple compute nodes. But we are using shared memory parallelism to also help parallelize the computations within each of the sockets. Now in this particular case, we've shown one specific configuration with hybrid parallel. Right? Here we've got 2 processes per compute node with 32 threads per process. But with hybrid parallel, you really can explore different configurations. You could run 4 MPI processes per compute node and use less threads per process. You could do 8 MPI processes per compute node, and so on and so forth. Herbert, why don't you please share some of the value that you see with hybrid parallel?
Well, On the one hand side, you have a few more knobs to turn to optimize the performance of your simulation. It's something that needs a little bit of experience for optimization, but the message should be that if you have a lump of material that doesn't have a lot of contacts in it, you should probably run best when you run it single-threaded. However, when you have a rather small model and a lot of hardware to run on, it's an option to run with, let's say, 2 or 4 threads in parallel to achieve a better performance than running single-threaded. Depends a little bit on how large the model is and how much work is to be done for each compute core or each thread on your hardware.
Okay, so this slide shows the memory required to run an engine benchmark model using different numbers of CPU cores, along with activating hybrid parallel using different numbers of threads per process. So here what we can see in the lightest blue color is the distributed memory parallel memory required. As the core count increases, the memory requirement increases significantly. So one of the benefits, as we just mentioned, to hybrid parallel is that we can use less MPI processes, and therefore we can reduce the total memory that's required while still activating, here we call it NT2 or NT4, that's 2 or 4 threads per process, that then effectively makes use of the same number of cores as the pure distributed parallel simulations, but it can allow the customer to reduce the memory that's required. And so that's shown with the dark blue. And that memory savings can be significant, not so much at 32 or 64 cores, but certainly as you get up into the hundreds or 1,000 cores, the memory reduction with hybrid parallel is significant. Right, so this slide shows a benchmark model that we ran on a cluster at Intel. So here we're solving a 50 million degree of freedom turbine model that's got, it's a nonlinear analysis, it's a static analysis with large deflections. It does 20 equilibrium iterations. It has bonded contact pairs. And we are solving this on a cluster at Intel called the Endeavor cluster. And here it had 2 Intel Xeon processors on each compute node, a total of 48 cores on each compute node, 192 gigabytes of RAM, Linux, and Mellanox and HDR InfiniBand. So we ran this a couple years ago, 2022 R2, on thousands of cores, starting with pure distributed parallel, so running 1 thread per process. And by the time we got up to around 6,000 to 8,000 cores, the scaling had stopped and the performance had started to actually slow down. So the benefits here of hybrid parallel was really kind of enabling us to find a good or best configuration or balance between processes and effectively turning on multiple threads per process to still utilize all of the cores on each compute node and sort of shoehorn this large simulation that was very resource and computationally demanding onto this fixed cluster resource in order to achieve the maximum performance we could get within that available hardware. Okay, so in addition to that turbine benchmark, Herbert, you have some experience in running very large simulations on your cluster, and you've been able to use hybrid parallel in a similar fashion.
So for that particular simulation, we had access to a cluster that had 1 terabyte per compute node, so it's about 5 times what Jeff mentioned on the last slides. In total, 30 terabytes of RAM on a machine that has 1760 CPU cores. And we organized the hardware in the way that we had 110 parallel processes with running 16 parallel threads, simply because although having 30 terabyte of memory is quite a bit, it would not be enough to run a case of this size without paging to hard disks, meaning running this thing in core was only possible with running multiple threads and reducing the number of parallel processes. On the other hand, when we did that, we could solve this 500 million degree of freedom case, which requires around 100 petaflops for a single iteration. We could provide enough memory, also this resource was rather limited, and successfully solve such a model without leaving the cores idle that had not been used for a single process. So in the end, all CPU cores of this cluster had been used, and this was an in-core solution that finished in the shortest possible time for a model like this. Benchmarks on different hardware platforms or different software versions, it's rather unusual to have them in a single slide, meaning that for what I try to show here is having different models, but on the latest version of hardware available to us, the Sapphire Rapids Xeons, and it's all run on 128 cores with 4 nodes times 32 processes. and using different mechanical APDL builds between 19.5 and 24.1. And I mean, what you can see here again, it's a log scale on the vertical axis that going from here to there is a factor of 2 in performance. And of course, not for each and every case, but when we go through a suite of cases that we typically use for benchmarking, it's apparent that you have cases where you gain a factor of 2. Sometimes it's a little bit less, but over the years, over 5 years of development, you see a nice speed up when using the latest version of the software that's available. That's mainly coming due to improved message passing or improved contact handling. But in the end, you can have an opportunity to gain as much as a factor of 2 just from using the latest build of the software.
All right, so this is a really cool slide that really highlights some of the long-term studies that have been done between Ansys and MicroConsult over the years. So again, we have this long-standing 15-year partnership, collaborative relationship where we've been working together on high-performance computing for mechanical simulations. And so Herbert's been tracking the performance of one of his benchmarks for almost 15 years, or over 15 years now. And this table really highlights that. So Herbert, why don't you give more details about this?
Okay, so actually this goes back to an actual customer project that we did in 2008. And the simulation, it's actually 3 different ones. We start out with the thermal simulation, use that thermal temperature field as an input for a thermomechanical simulation. And in the end, a submodel gets boundary conditions extracted from that thermal mechanical model to do a creep strain analysis on a little piece of PCB with an integrated circuit on top of that. When we started doing this simulation, it took about 2 weeks to complete a complete sequence from the thermal simulation to the creep analysis. And at that time, we had only like a workstation capable of doing these simulations, and it took 2 weeks to complete one sequence. And in the upcoming years, going from 2008 to 2023 and changing both the hardware platform and the number of available cores to do that simulation, we have been able to speed up that simulation from 2 weeks to about half an hour. So this is a speed up of around a factor of 600. And it was made possible by improvements in the hardware and also improvements in the software that allowed us to run this case on more than 1,000 cores and solving it within a factor of minutes for the thermal simulation and also for the submodel. The full simulation took the longest, but still everything together combined is about half an hour compared to 2 weeks when we started out in 2008. There's a few guidelines in running simulations on large models. The first part would be the hardware. The use of optimized hardware and a balanced hardware is absolutely critical. If you haven't already, then please listen to the first part of our presentation sequence that deals with choosing or making the right hardware choices. It's really a must to have balanced hardware and a fast interconnect. The other major point is memory provisioning. So usually you don't change the amount of memory put into your cluster after designing and building it. So at the beginning, when the cluster is assembled, the memory is being set and you can hardly have enough memory in your machine. As a general recommendation, it's better to run with lower process counts to avoid increasing memory requirements when running single-threaded and using all cores in your machines. I/O-bound jobs typically do not scale well as the I/O bottlenecks solution times.
Right, so in addition, Herbert, to the hardware considerations, anytime somebody's thinking about how well their mechanical simulations will scale with HPC, they also need to think about some software aspects. So, we've shown in this talk different forms of parallelism: shared, distributed, hybrid parallel. And so distributed parallel or hybrid parallel will almost virtually always scale better than just pure shared memory parallelism. But in addition to that, it's imperative that customers think about the size of their simulations. Okay, and so it's important to when you're scaling to higher core counts, to ensure that you have a large enough model to effectively scale to those higher core counts. And so our general guideline is that you need at least 2,000 elements per CPU core in order to achieve meaningful scalability. If you don't have enough computational effort on each MPI process, then the scaling will be limited. In addition to that, it's also important that you consider some of your modeling choices. And this is a bit of a sticking point because there is a lot of different analysis types and equation solvers and other finite element features within the mechanical APDL product. And these different features will all have some impact on the scaling of your simulation. And so it's just important things to think about is what sort of linear equation solver or what eigensolver are you using and how do those solvers scale? But also, what are some of the boundary conditions like contact or constraint equations? And these things need to be considered and thought about as they will impact the scaling of your finite element simulation within the mechanical APDL product. All right, so that concludes this talk for today. So thank you, Herbert, for sharing your expertise and your experience in using different forms of mechanical HPC. I certainly appreciate it.
Well, thank you for giving me a chance to talk about our experiences and for improving the software a little bit year over year.
Yeah, it's been a great collaborative relationship again. And so, yes, if you like this video, please let us know. We'd definitely be interested in hearing your comments or your feedback. And if you've been running mechanical HPC simulations, we'd love to hear about any such stories and share any insights you might have learned along the way. So again, thank you.